Welcome to Physics and Reality with Prof. Stuckey. I'm Emeritus Professor of Physics, Dr. Mark Stuckey, and today I'm going to show you the relativity principle at work in quantum entanglement. The only math I'm going to use here are the functions cosine and sine squared, so if you want to see the mathematical details, you can read our 2024 book with Oxford University Press, Einstein's Entanglement. Quantum entanglement has been called the greatest mystery in physics, but when you see how it obeys the relativity principle, it will be much less mysterious. To remind you, the relativity principle says, the laws of physics are the same in all inertial reference frames. My colleagues and I use the phrase, no preferred reference frame. You'll see exactly why in the following experiment. I'm not going to explain how the polarization-entangled photons are created. You can read those details in Dehlinger and Mitchell's papers cited here if you're interested. All that matters for our purposes is the behavior of these entangled photons. In each trial of the experiment, one of the entangled photons will be emitted from the source towards Alice's detector, and the other will be emitted towards Bob's detector. And as long as Alice and Bob don't put anything in their photon's paths, the photon will trigger a click in their detector. Photons emitted, photons detected. Photons emitted, photons detected. Here we see 8 trials of this version of the experiment, showing that Alice had 8 detection events, labeled with a 1, and Bob had 8 detection events. Now suppose Alice puts a polarizer in her photon's path. To remind you, according to classical optics, when you send unpolarized light to a polarizer, half the light is transmitted and becomes polarized along the polarization axis. That's the axis along which the electric field vibrates. So now what do you see? Well, a pair of entangled photons is emitted, and Bob's detector clicks, and in this trial, Alice's detector also clicks. Photons emitted, and Bob's detector clicks, but Alice's does not. Photons emitted, and again Bob's detector clicks, and Alice's does not. Photons emitted, and both Alice and Bob's detectors click. In 8 such trials, regardless of how Alice's polarizer is oriented, her detector has 4 clicks and Bob's has 8. Alice's 4 clicks are random. I've just organized the trials here. Note that 0 denotes a trial where the detector didn't click. Now suppose Bob inserts a polarizer, but Alice does not. Photons emitted, and Alice's detector clicks, and Bob's does not. Photons emitted, both Alice and Bob's detectors click. Photons emitted, and Alice's detector clicks and Bob's does not. Photons emitted, both Alice and Bob's detectors click. In other words, in 8 trials of this experiment, Bob gets 4 clicks and 4 no clicks, randomly, regardless of how he orients his polarizer, while Alice always gets a click. No surprise, right? It's the same thing Alice had. Now suppose both Alice and Bob have polarizers, and those polarizers have the same orientation. It doesn't matter what that orientation is as long as both polarizers have it. Photons emitted, neither detector clicks. Photons emitted, both detectors click. Photons emitted, both detectors click. Photons emitted, neither detector clicks. In other words, in 8 trials of this experiment, Alice and Bob each get 4 clicks and 4 no clicks in random fashion. However, their outcomes in each trial are always the same. This is due to the conservation of angular momentum. Now suppose their polarizer orientations differ by 30 degrees. What do we see in this case? Photons emitted, both detectors click. Photons emitted, Neither detector clicks. Photons emitted. Alice's detector clicks and Bob's doesn't. Photons emitted. And Bob's detector clicks and Alice's doesn't. In other words, we see all four possible outcomes. Alice 1, Bob 0. Alice 1, Bob 1. Alice 0, Bob 1. Alice 0, Bob 0. In the 4 trials that Alice got a click, Bob got 3 clicks. So in the 4 trials that Bob got a click, Alice got 3 clicks. This table organizes the trials according to Alice and Bob's perspectives to show this symmetry. Here is what you get when the polarizer orientations differ by 45 degrees. Now Bob gets 2 clicks for Alice's 4 clicks, and vice versa. And here's what you get when the polarizer orientations differ by 60 degrees. Now Bob gets 1 click for Alice's 4 clicks, and vice versa. Finally, here's what you get when the polarizer orientations differ by 90 degrees. Now Bob gets 0 clicks for Alice's 4 clicks, and vice versa. So how do Alice and Bob explain these data? Well, to remind you, when you send polarized light into a polarizer oriented at angle phi, it's called the analyzer here, relative to the light's polarization, the intensity of light is reduced by cosine squared phi, and the light that passes is now polarized along the analyzer's axis. From Alice's perspective, had Bob oriented his polarizer in the same direction as her polarizer, he would have gotten a click in the same 4 trials that she got a click because of conservation of angular momentum. So when Bob oriented his polarizer at 30 degrees from hers, he should have gotten cosine squared of 30 degrees, or 3/4 of a click, in those trials where she got a click, and sine squared of 30 degrees, or 1/4 of a click, in the trials where she didn't get a click. But there are no fractional clicks, so instead he gets clicks in 3/4 of the trials in which she got a click, and in 1/4 of the trials that she didn't get a click. Notice, and here's where we see the relativity principle, that Bob can make the exact same claim about Alice's data relative to his, and sure enough, when he organizes the data per his outcomes, it clearly shows that Alice's outcomes need to be averaged in accord with the conservation of angular momentum. So we have this average-only conservation that's symmetric. Both Alice and Bob can make that same claim about the other's data. This also explains the data at 45 degrees because cosine squared of 45 degrees is 1/2. And this explains the data at 60 degrees because cosine squared of 60 degrees is 1/4. And finally, this explains the data at 90 degrees because cosine squared of 90 degrees is 0. In this case, it's not average only, it's explicit conservation that you can find. So that's a simple empirical example of the relativity principle at work in quantum entanglement. If you'd like to read more about this relationship, you can read our book, Einstein's Entanglement, or any of our published papers linked in the video description. You can also watch my video series on the book on this YouTube channel. The thumbnail is shown here.